Welcome. In this video lecture, I'm going to talk about the economic order quantity sensitivity analysis. So when we are saying the sensitivity analysis, so in which basically, welcome. In this video lecture, I'm going to talk about on economic order quantity sensitivity analysis. So sensitivity analysis means if I am going to order the wrong quantity instead of the optimal quantity, what is the effect is going on our total cost. So we want to see basically the robustness of the economic order quantity. So how we can do that? We know that the total cost in the inventory management is the total ordering cost plus total inventory carrying cost, or you can say inventory holding cost. And the total cost against the optimum order quantity is going to be equal to 2 into carrying cost per unit ordering cost multiplied by the annual demand square root, which we have calculated earlier. Okay, like we started from the total cost and we replaced the q with the optimum order quantity. Okay, and we simplified and we got that against the optimum order quantity we can calculate the total cost by simply using the square root of 2 into carrying cost per unit multiplied by ordering cost multiplied by the total demand. Okay, so if we simplify this one, we are going to see that the total cost against the quantity which we have ordered divided by the optimum order quantity is going to be equal to 1/2 into the optimum order quantity divided by the wrong order quantity, you can say, which is the Q. That is, instead of using the optimum order quantity, whatever else we are number using, plus Q over Q star. So we can use this maths relationship in order to identify how much effect is going to be on a total cost if we are ordering less optimum order quantity compared to the optimum order quantity, or if we are going to order more. Okay, so for that, I'm using example. So let's say if we have the annual demand, we have ordering cost per unit, ordering cost per order. Okay, and we have the carrying cost. Okay, so against that, we can say that the optimum order quantity is going to be 2 into C naught multiplied by D divided by CC. So that is basically 2 multiplied by 500 per order multiplied by 2000, okay, divided by 12.5. So we are getting the optimum order quantity number. Now, in order to perform the sensitivity analysis, what we are going to do is we have listed down the Q, that is the quantity which we may order. Okay, this is the optimum order quantity, which is 400. If I am saying that if I am going to order 200 more or 400 more, okay, almost double, 200 less or 20. Okay, so against that, against every Q, we have calculated the ordering cost using C naught into D divided by Q. Similarly, we have calculated the holding cost. If we sum them, we are going to calculate the total cost. Okay, so now we are want to check, okay, what is the effect on the relative change in the quantity. Okay, we are saying if the optimum order quantity is 400 and we are going to order 400, so that means the relative change is 1. That means there is no change. Okay, this is saying if we are ordering 50% more than to the optimum order quantity, okay, or if we are saying we are placing more than 200. Okay, so that is 200% more than the optimum order quantity. Right now we are saying 50% less. Okay, and so on, right? So similarly, we are going to calculate the total cost. So that is 1, or you can say 100%. So it is saying that if we are going to order more than the optimum order quantity, which is almost the 50% of the optimum order quantity, that is basically the 200. Okay, which means instead of ordering 400, we are going to order 60%, which is 50% more than the optimum order quantity. The total change in the total cost is going to be increased only 8.3%. Okay, so if we are going to order double then the optimum order quantity, that is 25% is going to be increased. That means 25% the total cost is going to be changed. If we are going to order less, this is saying 25%, okay, or over here it is saying that it's quite a large number. But as we can see that even we are going to order double or 50% less, so we can see that there is not a much change in the total cost. Okay, so now the question is, should we order more or should we order less? So as we have seen earlier, if we are going to order more quantity, there will be a less change in the total cost compared to if we are going to order less. So this is indicating if we are going to order the less compared to the optimum order quantity if we are going to order more. And you can see the robustness of the EOQ model. So over till now, over here we can see that there is no change in the total cost. Okay, now I am moving towards if we are going to change the demand, which means instead of using the actual demand, actual forecasted demand, actual demand, we are using the forecasted demand, or you can say that we have done some wrong forecast, whether we have done the over forecast or if we have done the under forecast, what is the impact going on our total cost. So how we can do that? I am using the annual forecasted demand or the actual demand, and based on the forecasted demand, we have written down the optimum order quantity. Obviously, the only change in the demand, that is a forecasted demand or the actual demand, and I am using again the same relative function of the optimum order quantity. Okay, that is basically the forecasted demand compared to the actual. Okay, this is going to be equal to this one. Okay, if we put the formulas over here and add them, if we simplify it, we are going to see that this is going to be equal to this one. Okay, now we can see that the relative change in our actual forecast to the actual cost, actual demand forecast cost to the forecasted one. Okay, so over here we have the demand, we have the ordering cost, we have the carrying cost, and over here we have the actual demand. Okay, if this is the actual demand, we are saying that, which is basically the 2000, and here we are saying that we have forecasted the 2000. So that's why quality against the actual demand and quantity against the actual demand and quantity against the forecasted, the ratio is going to be 1, and total cost ratio is also be going to 1. Now, if we predict more, okay, that means we have over forecasted the demand. Okay, the actual demand is 2000. The actual demand is 1800, but we have over forecasted, and we can see that this is the value is going to be less than 1. Okay, so we have over forecasted. Okay, that's why this ratio is going to be small. If we have under forecasted, the value is going to be high. Okay, so similarly, that is also against the optimum order quantity which we are going to should order. But if we see the impact on the total cost, you can see that even if we under forecast 50% or over forecast up to 50%, we can see that there is no change in the total cost, or a very small change, which is approximately 6% more. Okay, compared to the optimum cost. Okay, that is a total cost. So that means, what if it is going to be changed on carrying cost or ordering cost, there will be not a such impact on if the demand is going, we are going to under forecast or the over forecast, that the mean difference is only the 6%. Okay, as you can see from here, the total cost is quite a robust, which is basically almost equal. Okay, if we are going to under or the over, okay, based on the forecasted demand or the actual demand perspective. Now I am going to talk about the order cycle time. That means how sensitive the total cost to the T. Okay, that means why do we care? What is, why is the time different? Okay, how do I find out the best T? That is also the practical. If I'm saying demand, ordering cost, carrying cost, so based on that we have calculated the optimum order quantity as well as the total cost, and the T star, that is the time between the order, is going to be Q star over D, which is 2.5 years. If we are going to multiply with 365 days, that is 73 days. Okay, or if we convert these days into the week, that is 10.4 week. Okay, so that means the T star is Q star over D. So that means the Q star is going to be D into D star. Again, I am using the relative relationship of the order quantity and the order quantity of with respect to the total cost. We can see that is going to be this one. If we replace Q with DT and Q star with DT star, so we are going to get this one. Okay, that is the change in the time, okay, and the effect on the total cost. So right now it is saying that although the optimum star is every 10.4 week we should order, and how much we should order, that is 400 units. So right now if it's saying if I order every week instead of 10.4, okay, so that means my total cost is going to be increased 524%. Okay, if I am going to order every 4 weeks, that means the cost is going to be increased 49%. So what optimum time order we can use? Okay, for that, that is very powerful policy which is known as 2 power k policy. So it is saying order in the interval of power of 2. Okay. So select the realistic time period whether you are going to find out the time between the order in days, weeks or months. Okay. And you will see that with the power of 2 power k policy, your total cost is going to be higher, maximum up to 6% if you are using 2 power k. Okay. So what's the interval? That is 2 power k is less than or equal to the optimum star value is less than or equal to 2 power k plus 1. So pick that k against in between where the T star is going to be lie. So as we have calculated using the previous data, the T star is 10.4. So that means if I am going to use k is equal to 3, so 2 power 3 is going to be equal to 8, and 2 power 3 plus 1, which is 4, that is going to be 16. So that means 10.4 is going to be lie between 8 and 16. So that means which number we should pick. So the normal rule is you should pick with the smaller k. That means we should pick 8. So that means every 8 week, okay, because the base period we are picking, that is a week. So every 8 week I should order the quantity. Okay. So let's see why we are picking the 8. So as you can see that we are saying the T star must lie, okay, between 2 power k and 2 power k plus 1. So in a worst case scenario, so ultimately we want to reduce this error. Okay. So in a worst case scenario, this T star could be exactly equal to the half. That means if I am saying the k is equal to 3, so the 2 power k, that means 2 power 3, okay, and 2 power 3 plus 1 is going to be 4. So the center is going to be 2 power 3.5. Okay. So in a worst case scenario, it might be possible they have the same difference. But in the most of the scenario, what we want to see is that is we want to pick that particular number where this gap is the smaller one. Okay. So that is why we are saying that find the lowest value of the k that satisfies this one. Okay. So, if we see in our particular example, we have seen that we should pick k is equal to 3 because 10.4 is going to be near to the 8 compared to the 16. So, that's why we should order every 8 week. And mathematically, we can prove that the total cost or the total cost change is only the 6%. So, how we can do that? We know that from our previous this one, that relative cost against the time and the optimum time, the relationship is equal to this one. Okay. So if I'm going to use t, that is going to be equal to this one. If I'm going to use 2t, so in place of t, so that is going to be this one. If we do the equal, because we want to minimize the error in order to find out the relationship between t and t star, So if we do simple maths, okay, and we are getting that the t star is going to be equal to square root of 2, whereas t by t star is going to be 1 over 2. Okay, so that means 2 power k. So against, because we are finding 2 power k policy, so total cost 2 power k divided by total cost against t star should be less than or equal to, that is this one. Okay, which means that is going to be this one. Okay, so which is basically 1.06. So only 6% our total cost is going to be changed if we are using instead of the optimum time we are using 2 per k policy. Okay, which we have seen that for our example we should order every 8th week, right? So even you can calculate from here as well. So the t star is 10.4 square root of 2, 2 power k, okay, is going to be less than or equal to square root of 2, and the t star is 10.4. Okay, and you can calculate this number. So thank you so much. See you in the next video.